the thermal conductivity we have known so far, but it has to be continued, and it is going to establish so many relevant relations regarding the conduction of heat, like thermal resistance, like temperature of interface, like combination of series and parallel of conductors. So all these we are going to derive and find in terms of thermal conductivity K. You must know what is thermal current. This is rate of flow of heat. This might be said as joule per second, and you must remember that this could also be written as watt. So watt is also the unit of thermal current. Normally we say it is the unit of mechanical power, but you could also measure thermal current in terms of watt. You see this relation Q equal to Ka delta theta T upon L. Q by T you could say H. So you get the relation H equal to Ka delta theta upon L. It is the temperature difference and it is the distance. Suppose this is the part of conductor and this is distance delta L. Temperature difference between the two ends is delta theta. Then this ratio is also known as temperature gradient. That is the temperature difference per unit length. Temperature gradient is delta theta upon delta L. This is called gradient, you might say, temperature gradient. Now in this place, if we use the term temperature gradient, then we could use this whole relation with negative sign simply because the heat always flows from higher to lower temperature. That means with the advancement of the thermal current, the temperature regularly decreases. That's why in most of the cases you'll find minus sign also. That is very much justified. You see, now we'll see how the thermal resistance is defined and how do we get the equivalent value of thermal resistances. Suppose it is electric resistance, then in that case, this is the relation rho L by A, or you could say L upon sigma A. Sigma is a specific conductivity, whereas this rho is known as thermal resistance. Sigma is analogous to thermal conductivity, already we know. Here, this thermal resistance will be defined as L upon K A. This is thermal resistance. Thermal resistance. But we have to remember that thermal resistance in electricity is defined by potential difference upon current. Normally, we don't write delta I. This is mostly written as I itself. But here in case of thermal current, in place of potential difference, we are going to use delta theta, and in this place, we are going to use the thermal current. If you take the ratio of delta theta and H, already this is given by delta theta upon L. You see, if you take the ratio delta theta by H, it's going to be L upon Ka. That is what exactly we have written. So you get this relation for thermal resistance. And finally, now we'll try to define the temperature of interface when two conductors are joined together. You see, suppose two conductors having temperature theta 1, theta 2 this way. This is given here. You see T1, T2. The interface of the common phase. Our aim is here to find the temperature of this interface. This is the thermal flow or rate of flow of heat. Here also H1 and H2 are representing the thermal current, you might say, and their lengths are L1, L2. Because in a steady state, you see the rate of flow of heat is always going to be equal. If we put the values of H, that K A delta theta upon L1 by using this relation, since they have been used in series combination, area will necessarily be equal, and if area is equal, the two would be cancelled. This is suppose having K1, this is K2, and delta theta is also going to have different value. This is theta 1 minus theta. Here it will be theta minus theta 2. If you solve, you are going to get the final value of temperature of interface. This could be written as K theta upon L theta, or you could say T also here, upon sigma K upon L. Now, if there are two, you could say K1 theta 1 upon L1, K2 theta 2 upon L2. Similarly, here K1 upon L1, K2 upon L2. By elaborating, you will get this form, and it is the temperature of interface. Then what is going to be the equivalent value of thermal conductivity? You see, this is the formula for temperature of interface. The equivalent thermal conductivity, if you connect them in series, one condition will be pre-imposed that area remains same for both. In that case, the equivalent thermal conductivity is going to be sigma L upon sigma L upon K. It is irrespective of the number of conductors. You might use any number of conductor, L1 plus L2 plus L3 and so on. Here also L1 upon K1, L2 upon K2, that is given here exactly. Then, if it is a parallel combination, automatically the condition imposed shall be that they have equal value of length here. In that case, the equivalent thermal conductivity is going to be sigma Ka upon sigma A. Here they will be having equal length, but area might differ. Say it could be A1, A2, A3 and so on. So it will be in the form, K1 A1 plus K2 A2 plus so on, divided by A1 plus A2 plus A3. That is the equivalent value of thermal conductivity in parallel combination.